A student mixes 40 milliliters of 0.1 molar hydrobromic acid with 60 milliliters of 0.1 molar potassium hydroxide at 25 degrees Celsius. What is the concentration of OH ions of the resulting solution? I've went ahead and drawn the reaction here to show you what is going on. Recall that hydrobromic acid is a strong acid, whereas potassium hydroxide is a strong base. This means that both solutions will dissociate 100% in solution, which I have shown by this one direction arrow here, as opposed to an equilibrium arrow which shows both directions. Therefore, we will write both solutions as their respective ions and anions, H plus and Br minus, and K plus and OH minus. For our products, potassium bromide is a soluble salt, meaning in solution we will also have K plus and Br minus. From here we can write our net ionic equation. To save some time, I went ahead and canceled out the spectator ions and wrote out the net ionic equation. The resulting net ionic equation is H plus and OH minus react to form H2O, or H3O plus OH minus equals 2H2O. Make sure to balance the H's if you use H3O plus. Knowing that the reactants react to completion and that the net ionic equation reacts to form water, we can solve the rest of the problem. The next step is to calculate the molarity for each solution. 40 milliliters of 0.1 molarity hydrobromic acid and 60 milliliters of 0.1 molarity potassium hydroxide. The molarity equation is equal to moles over liters, which I have demonstrated over here. 0.1 molarity equals X over 0.04 liters, which is equal to 0.004 moles of hydrobromic acid. Repeat the same process for potassium hydroxide to find that there's 0.006 moles of potassium hydroxide. Now, notice that hydrobromic acid is a strong acid, which means that we actually have 0.004 moles of H+. It is the same for potassium hydroxide. We actually have 0.006 moles of OH-. If we look back at our net ionic equation, the 0.004 moles of hydronium ions are going to react with the 0.006 moles of hydroxide ions. Here I've written out the net ionic equation with the values of the moles we just calculated put into the initials of the ICF table. Now, since we only have 0.004 moles of H3O+, all of it is going to react in the equation, which means that we will subtract 0.004 moles in the change part of the ICF table. Since this is a 1-to-1 mole ratio, we will also subtract 0.004 on the other side of the C table. Now, to find the final value, we simply subtract the values to find that moles of OH- is 0.002 moles. Now, since the question asked for the concentration of OH-, we're going to have to use the molarity equation again. So, molarity is equal to 0.002 moles OH over 0.01 liters. Now, the reason it's 0.01 liters is because this is the total amount of liters in the entire solution of the strong acid, strong base. And this is going to equal 0.020 molarity for the concentration of OH-.